Okay, in this video I'm going to finish the proof of proposition 6 from the review portion of our handout 1. So what are we trying to show? Well, we're trying to show that these conditions on a function f mapping x into y are all equivalent, namely f is 1 to 1, which according to our definition means that f is 2 to 2, as we said. Distinct points in x map to distinct points in y. That's equivalent to this condition here. If f maps two values, x1 and x2, to the same value in y, then x1 and x2 have to be the same to begin with. And then the last condition was that if f is 1 to 1, then for each y and y, the preimage of the singleton set y under f has at most one element, and conversely. Alright, so first of all, one if and only if 2, well, as discussed in class, statements 1 and 2 are in fact contrapositive statements of each other, and therefore they are logically equivalent. So in fact we have nothing to prove there, so let's move on and prove the equivalence of statements 2 and 3. Alright, so first of all, 2 implies 3. Okay, so what do? Well, we suppose statement 2 holds. Okay, so what does that mean? Well, we're assuming that whenever f maps x1 and x2 to the same value in y, then x1 and x2 actually had to be the same. And what are we trying to do? We're trying to show that statement 3 holds, which is to say that given any y and y, the preimage of the singleton set y under f contains at most one element. So, to prove 3, let's take a y and y and try to show that the singleton preimage of this singleton set has at most one element. Well, how can we do that? Well, we'll pick potentially two elements, x1 and x2, in this set and show that in fact x1 has to equal x2. So, in other words, we're going to let x1 and x2 belong to the preimage of this singleton set y. Okay, and we're going to try to show that x1 equals x2. Alright. Well, what is this set? First of all, well, it's the set all x in x such that f of x belongs to that singleton set y, which in this case just means that f of x equals y. Alright? So, what do we need to do? Given potentially 2 points, x1 and x2 in here, to show that this set has at most one element, we just need to show that x1 equals x2. So we're trying to show that x1 equals x2. Well, we just said that if x1 and x2 lie in this set, then f of x1 must equal y, and f of x2 must equal y. Alright, so then f of x1 equals y, and f of x2 equals y. So we can write it like that. Well, what does that mean? That means that f is taking x1 and x2 to the same value. But we're assuming our statement 2. Well, what does statement 2 say? It's going up. Again, statement 2 says exactly that if f of x1 and f of x2 are the same, then x1 is x2. So, in this case, we get to conclude that x1 is equal to x2. Okay, so get to conclude that x1 is x2. So, from 2, x1 equals x2 as needed. Okay, so the last thing to show is that statement 3 implies statement 2. In other words, we're trying to show that if, for any y, the preimage of this singleton contains at most one element, then this condition here is satisfied. So what will we do? We'll suppose, so we're going to assume statement 3, and we're going to suppose that f of x1 equals f of x2, and try to conclude that x1 is equal to x2. That's our plan. Right, so down here, we assume 3 holds, and that f of x1 is equal to f of x2, and we'll be done if we can conclude that x1 is equal to x2. Alright, so let's just call this common value that f takes at x1 and x2, let's call that common value y. So let's say y is equal to f of x1, which is equal to f of x2. Well, then, certainly, x1 and x2 both belong to the set of all x such that f of x is y. Right? F of x1 is y, and f of x2 is y, so x1 and x2 belong to the set of all x's for which f of x is y. But what is this set? This set here is just the preimage of the singleton set y, right? This is the same, of course, as saying that f of x belongs to this singleton set y. But what are we assuming? Well, we're assuming statement 3. In other words, we're assuming that any single one of these preimages has at most one element, and what do we know? Well, we know at the moment that x1 and x2 belong to this set, which can contain at most one element. What can we conclude? x1 certainly couldn't be distinct from x2, otherwise we would have more than one element in the set. x1 therefore must equal x2. So we can say from 3, we must have x1 equal to x2, and that's what we wanted to show. We wanted to show that if f of x1 is f of x2, then x1 is x2. That means that f is 1 to 1. And we are done.